Good afternoon, everyone. Welcome to the 11th week or second last week of the live tutorial session for the points at topology course. So, in this session, we will discuss some problem related to topological groups, which is the main topic of the assignment 12 for this week. So, let us start with this one. So, if A, B are two symmetric neighborhoods of E, so everything happening is in a topological group G, where E is the identity element of that group, and AB are AB are two subset in the topological group G. Then we need to show that A closure union B closure, that is contained in AB intersection BA. So ABB are just so using the multiplication in the group G, AB consists of all points A dot B. For A belongs to A, B belongs to B, and similarly for BA. So for this one, how to proceed? Anyone have any idea? So can at least someone recall in a topological group closure of a set how it is represented through symmetric neighborhoods of E? Then this is automatic.
It's intersection of all the symmetric node. A closure is intersection of A with B. If V are all intersection is over B, where V is a symmetric neighborhood of B.
Exactly. So in this case, as AB are already symmetric neighborhoods of E, so basically that A closure, or in particular B closure, both it is intersection of all V belongs to, let's say, S, where and this is AB, or this is same as also intersection of V belongs to S VA, where S is the set of all symmetric neighborhood of E. So in this case, it is actually indeed true. Instead of taking symmetric neighborhoods, it is also true for any neighborhoods of E. So that is also same as this A closure. So in particular, I can say that thus A closure is contained in AB, and also A closure is also contained in BA, as B belongs to this set S. And similarly for B closure, I can use A belongs to S, so this is contained in AB, and B closure is also contained in BA, as A belongs to S. Thus A closure union B closure. So both the things, A closure is also contained in AB intersection BA, and B closure is also contained in AB intersection BA. Maybe I should write that. This A closure is contained in AB intersection BA, and B closure is also contained in AB intersection BA. This implies A closure union, if I take, that is also still contained in AB intersection BA. Okay, so this is pretty easy. Just using this closure thing for in a topological group. Okay, so and this is also not hard to prove. You just have to use basically you can see that if X is an element for a closure, or just this is actually AV intersection A, this is empty if and only if you just analyze this one, then automatically X does not belongs to AB or VA, either way. Okay, so yes, so using this one you can actually prove if X does not belongs to A closure, then that will imply that X does not belongs to AB for some B, so that means it does not belongs to also intersection. And similarly, if you assume that it does not belongs to the intersection, that means there exists some V such that that element does not belongs to AB. Once that does not belongs to AB, so that means X V intersection A is phi, that means that does not belongs to A closure also. So you just have to use this one to see both of this. Okay, so this is done. So let's go to the next one. So suppose G is a topological group, and to prove the following two things. So first, a subgroup generated by an open set is always open, and second one is if a subgroup contains a non-empty open set, then the subgroup itself is open. Okay, so solution. So subgroup generated by an open set, so let's say A be an open set, in G, then I want to prove the subgroup generated by A means you consider this let's say B equal to union over all n belongs to let's say n greater equal to 0 and A power n, right? So you consider all those A power n is already like product of n elements, each of them belongs to A, so that all such elements consist in lies in A power n, and A power n consists of all those elements. So you consider the union of all those, then that will form a subgroup of this group G, and that is called the group generated by this set A.
Sir, can you please explain this part one more time? Why B is union of A?
Okay, so I'm basically defining my B to be this union of all those A power n, and I'm saying that this will this is the set, basically this is generated by this A. Now this will actually form a subgroup also. So why? So if you pick let's say any two element from here, then if you just multiply them, or okay, maybe just for these to be subgroup, we need this map, right? So basically it is probably noted as new, so that if I say that this B cross B to not B but G, it is defined by let's say x comma y gets mapped to x inverse y. So if this map, so if gamma of B cross B, I can say if this is contained inside B, then we say this B is a subgroup, right? So you basically consider all those now if you take two elements from here, so it is either product of sub so one x belongs to, so x will be probably some a1 through ak, and another element is, let's say, b1 through bl. Okay, all those ai and bi all belongs to a. Then this gets mapped to this inverse a1 dot ak inverse b1 through bl, right? And now if you maybe I need to consider a, okay, you can also include those minus power also, maybe that is easier. So you can consider, instead of n greater equal to 0, you basically fix n belongs to z. So a inverse, again you take a inverse and respective power of a inverse. A inverse consists of all inverse element of those things, and then you consider this set. So this is actually group generated by a. Okay, so here if you just see that this thing, so this is clearly belongs to here, because it is ak inverse dot a1 inverse b1 bl, right? And this is an element of this b, because here a1 through all of this thing belongs to, okay, I actually don't need this belongs to z also, it is fine. All this a power k inverse, those thing belongs to that may not belongs to a.
So are we proving why B is equal to union of AN, or are we proving it's a subgroup first?
No, basically the subgroup generated by an by any set, that means you consider all the possible power of the elements of its element, and then that will, like, if you say subgroup generated by an element a, this is basically it consists of all a power n such that n belongs to z, or n belongs to basically n greater equal to 0. That is also fine, but you can take n. So this set. Now if you just check this property, that a power m and a power n, that will get like a power n minus m, and that is again still belongs to n belongs to z. So that belongs here, so that basically closed under this map, hence this is a subgroup. Similarly, if you do the same thing here, like in this group B, then I'm also saying that this is still a element in like this gamma is closed under closed in B. So if you consider this operation, then it is still an give me an element of this B. That's my claim. Okay, it is like in this case there are only one element in this case, but in A you might have many elements, so you individually you can take any power of them, as well as you can take like different element, and they consider all possible product of those. So here that's why I tried to I'm trying to show that this B is actually a subgroup. Okay, so which is subgroup? Maybe I need to further okay, maybe I need to further subdivide this. It's like, okay, you can just take, instead of this thing, I can take n greater equal to 0, a union a inverse, okay, and then power take power to bl. Then it is fine, right? So here basically all those things belongs to this belongs to some a1 through ak, all those belongs to some a union a inverse. Basically I just symmetrize my a and a inverse, so that I can say that this a k inverse a1 inverse b1 through bl, all those belongs to my a union a inverse, because b1 through bl and a1 through ak, all those belongs to a. So inverse thing still it is belongs here, and hence if I take the multiplication this thing, so this is basically belongs to a union a inverse power k plus l. Okay, so in particular this is subset of b, so this belongs to b. So that means gamma b cross b is contained inside b. So is this clear? Like to show any like anything is a subgroup, you have to check that if you pick two element from the set, so in particular this x and y belongs to my two arbitrary element in b, and then if I can show that x inverse y belongs to b, then it is a subgroup of the ambient group G, right? So in this case, that's why I'm proving that this map is actually contained inside B. If I can show that B cross image of the map, image of B cross B under this map is contained inside B, then it is a subgroup. So A1 through AK and B1 through BK BL, so this is an element of it belongs to B, so it is belongs to some power of A1 union A union A inverse sum. So I pick basically this is belongs to A union A inverse power K, and this belongs to A union A inverse power L, and I just multiplied, I see that this is belongs to A union A inverse power K plus L, right? So if A were given to be symmetric, then I don't have had to take this A union A inverse. Okay, so is this clear now?
Yes.
Okay, so
but we just prove it subgroup, not generate.
No, it is generated by A, right? All the elements.
Due to its,
huh?
Due to its definition only.
Yeah.
How we.
Yeah. It is by definition the subgroup generated by a set A is defined like this. Okay. So now I have to prove that this B is actually open. That's what the question says, that A is generated by an open set. So this B is the group generated by A. Okay. And now
but
you.
Now B is open only because A was open. So this inverse will also be open. And
yes.
Finite union and then that.
Yes, exactly. So that's the thing. So okay, this is the thing, that this is thing. Now A is open, so as A is open, this A inverse is also open, is also open as basically as this inverse thing. So G to G, this G going to G inverse, this map is a actually self homeomorphism of G, is a homeomorphism. So under this thing, so this particular in particular this is open, so A inverse is also open. So A inverse is open, so A union, this implies A union A inverse is open, union of two open set, and this implies A union A inverse power anything, power n is also open. So why that is like any power is why it is open? So why power open set is still open?
Okay, sir.
Yes.
It's group, so therefore that binary operation of
Yes, binary operation is thing, but here again actually this is due to
no. Actually, we proved that because in class also we proved that this is also a homeomorphism G cross G going to G, where we map X, this tuple XY to X into Y.
no, that is not a homeomorphism. Like varying a G cross G to G, that is not a homeomorphism. Like simply if you
That was
no, simply this is like you are saying R cross R is a group, R cross R is homeomorphic to R. That is not true, right?
no.
That is particular left multiplication and right multiplication are homeomorphism. You have to fix one element and then multiply with G. So basically this is the inversion map, and something come up with this. Okay, so this is the inversion map, and the left multiplication by any element, say H. So this is G to G is defined by G going to multiply H on left, so Hg, or right multiplication Rg, Rh, so G goes into H, Gh. Both are again homeomorphism of G. So that implies that if you in particular you can say that A union A inverse, that going to H times A union A inverse, that is open, as this is open. So you can now vary this H for all elements of A union A inverse, and A union A inverse square is nothing but union of all these sets. So that being union of open sets is open. So similarly it is for 2. Now you induct will be proved for any n, right? Is this clear?
Yes.
Yes. So here basically for first one is just inversion is homeomorphism. Next one is the right multiplication or left multiplication. Both are again homeomorphism. So that's why. So once this is open for all n, then this implies union of this open set. So B is open. Okay. So subgroup generated by open set is open. Okay, so next basically we have if a subgroup contains a non-empty open set, then it is open. Let H be a subgroup of G, and H contains a non-empty open set, and let's say U not equal to phi U. This is open, contained in H. Okay, maybe I just this open, U open in G. Okay, so we need to prove that H is open. Okay, so any idea how to prove this one? So two things you have to use. Once this is subgroup, and then U contained in H. So Can you write H as union of open set using this open set U?
So as we did in the previous question.
Did like in this case you don't have to make this H as subgroup. H is already given to be subgroup, and U is contained inside H. So you can say,
If I'll take union of U, then intersection with U inverse power n.
yeah, that is contained inside H surely, no problem. But I want something that H is union of open sets. Those are not all of like, how do you guarantee that is all of H?
Then I have to take complement of U in H.
Complement of U need not be open, right? That is closed actually.
Closed.
So better you actually have like, you can use the left translation or right translation, anything. So if you consider this HU for any H belongs to H, so this is an open subset, and that is belongs to that is contained inside H because H is a subgroup. U contained inside H, and you are just left translating that set by an element of H. So this is clearly contained inside H. So as H is a subgroup, for any H belongs to H times U, that is contained inside, and definitely H, okay, I don't know H belongs to that set or not. Okay, is that as a content just non-empty open set file. So H belongs to H, and HU, that is contained inside H, right? So then, like, I want to say that this H equal to actually union over all those HU. H belongs to H. Now can I say this one? If I can say this one, then I'm done. U being open, HU is open. So why this is true?
So because this union is already contained in H.
Union is content. Yes, so this containment is clear. Yeah. Why?
Yes, other way around. If I take any element in H, then corresponding to that element, H will be bounded. It's just a subset.
Yes.
I just have to prove identity.
Yes. Yeah, that is enough. That if you can prove that identity belongs to some HU, then you are done. Now can you use non-emptiness of U somewhere? I haven't used U is non-empty, so that you have to use somewhere.
Yes. And if I take any element here, then I can take its inverse, and then E will belong to it.
Yeah, exactly. So as u is non-empty, so you pick any, let's say u naught belongs to u, then you consider u naught inverse this small u naught. So u naught inverse u, this actually e belongs to this set. Once this belongs to this set, then you can, like, for any h belongs to h, you consider just h u naught inverse u. Then this element is like is an element of h, and so this will belongs to this collection, and h belongs to definitely here. So hence any h is contained here. Okay, so here basically you need to use that u is non-empty. So as u not equal to phi, so there exists u naught belongs to u intersection h such that e belongs to u naught inverse u, and this implies for any h belongs to h belongs to h u naught inverse u, and h u naught inverse belongs to h. So this clearly any h belongs to this collection. So, and as u is open, hu is open for any h belongs to h. Again, as this left translation as LH G to G, it sends G to HG is a homeomorphism. So thus H being union of open sets, it is open. Okay, so this completes this one. So let's go to the next one. Okay, so this is again related to the this compactness and Hausdorffness of the quotient space. So suppose H is a closed subgroup of a topological group G, and then the quotient map is always actually open map, and actually the closeness is not needed. If you have a topological group G and H is a subgroup of that, then the quotient map is always actually open map. So can you see why? So to show this is open mapping, what you need to show? If you pick a open set in G, you have to prove QH open. Yes. Okay, so let's pick an open set. Let U be an open set in G to prove this Q of U is open in G mod H, right? But Q, so on G mod H you have quotient topology, so Q of U that is open in G mod H, you can only if this Q inverse of QU is open in G mod H, right? But q inverse of q u. So what will be this thing? Can I write this as union of open set or something so that I can say this is open? QA consists of like points such that it is if you just if you add points, like what is the inverse image just of a single point. So q inverse of a single point, let's say this qy. What is this? This is all like translate of h, y translate of h, right? This is nothing but y. So if I just this cosenting this thing is as left coset or just yh. So this is nothing but just yh, right? All of this thing gets mapped to under q, this get mapped to qy, right? Because I'm cosenting by this h. So similarly, if I see here q inverse of qu, what will be this thing, this set? This set will be just UH, right? So for each you are taking union over all those YH for Y belongs to U. So it is just UH. So basically this is union over all U belongs to capital U, says UH. Or maybe the other way is I need, because I want to show this is union over open set. So as U is open, I should consider U, capital U, H, or H belongs to capital H. So again this right translation are homeomorphism. So you can say like you can say this as U is open and U is open and this right translate, let's say RH, G to G, G sends to GH is homeomorphism. This UH is open. Thus again Q inverse QU being union of open set, it is open. So Q inverse Q is open in G. That implies by cosine topology this QUH open in G mod H, and that's all you need to put. So that's Q is open, right? So here we didn't use anything like this closeness of this thing. This is always actually an open mapping, so closeness you don't need. Okay, so is this clear or is there any confusion? You just have to analyze what is the inverse image of a point or anything. So then you clearly see the inverse image is nothing but the union of open sets. Okay.
Sir, this
Yes.
inverse Q being union of open set, up to here it's okay. But why it implies Q of U is open in G by H?
No, that's the like on G mod H we have the cosine topology, right? So in cosine topology, what it means, and a set is open or closed if and only if inverse of that thing is open in the on the left hand side, right? So I wanted to show that this Q of U, that thing is open in G mod H. So that means I have to prove that Q inverse of QU is open in G
Okay, sir, okay.
just by cosine topology.
Oh shit.
So by G on G mod H. Okay, so that implies Q is open. Okay, so next we have that this G mod H, this with cosine topology, that is actually a Hausdorff space. So you have to use this H is closeness here. So can you like what you can prove to show a space is Hausdorff? So one, the basic definition is if you have two distinct points, there exists open set which separates those 2 points. So another alternative thing we already also have proved in some tutorial that this a space is Hausdorff if and only if the diagonal, if you consider the diagonal subspace of the cross product, like in this case if I consider the diagonal in G mod H cross G mod H, so it consists of all point x comma x such that x belongs to G mod H. That's the diagonal. So that is a closed subspace in G mod H cross G mod H. That also implies that this is Hausdorff. So that is an equivalent condition. So in this case actually we'll use that thing to prove that this G mod H is Hausdorff. Okay. So recall G mod H is Hausdorff if and only this set, the diagonal is denoted by delta, diagonal, this is let's say GH. So the elements of this set is look like GH. So GH comma GH belongs to G mod H cross G mod H such that G belongs to G is closed subset and the proof is again like not that hard. So Hausdorff means you have for distinct point distinct neighborhood. So I can actually that will imply that this complement of this set is actually open, because what is the complement? Complement consists of all the points G1H comma G2H such that G1 and G1H and G2H are not equal, right? And that is again you can once you have distinct point here, so you actually already have by Hausdorffness you have two distinct neighborhood that separates those two. Now if you consider the product of those two open set, that is open in G mod H cross G mod H, right? And that is properly contained inside this delta complement. So that implies this is open set, hence the complement of complement, so hence delta is closed set. And conversely, if you again assume delta is closed subset, that means delta complement is open, and that means for distinct, if you pick two distinct element here that belongs to delta complement, and in delta complement being open, you have some basic neighborhood which contains this those two distinct point as an element of delta complement, so that's contained inside delta complement. That means you have neighborhood around each of those point which do not intersect, because that contained inside delta complement. So anyway, both the things are not that hard. So in particular, in this case actually we use this Q map. So basically to prove this thing is a bit easier. Instead of checking this the Hausdorff for distinct point, to check this is closed subset, it will be a bit easier. Okay, you can just follow the proof of that thing and then get back to the distinct neighborhood, but I'll use this one. Okay, so now can anyone see why this is a closed subset here in this particular case? Why this delta is closed subset? Like, at least any idea like how to proceed or anything? Like, you can use the previous thing. That Q is a open mapping. Now can you prove this delta complement is open? So delta complement is a subset in G cross H, G mod H cross G mod H. So does that at least give any hint, or what should you what map you should consider?
If I take any element in delta complement, then that will be like G1 H, G2 H, and G1 is not equal to G2.
No, G1 not equal to G2, that is not the thing. So G1 H not equal to G2 H means G1 inverse G2 does not belongs to H, because that is a set, right? That is again a thing. Okay, so that I should mention. So note that. So G1 H not equals to G2 H. This is if and only G1 inverse or G2 inverse G1, anyway, so both the same. So this does not belongs to H. This you can easily check. Basically G1 H equal to G2 H if and only if G1 inverse G2 belongs to H. Because as I said, if it is belongs to H, then you can simply take this these two are set, then becomes equal. Because if you pick any element here, G1 G1 comma H, then you multiply this G1 inverse comma that thing, then it is belongs to some G2 comma G2 times H, some H, right? So that gives that implies this set belongs to the as a subset of G2 comma H. And so one G1 inverse G2 belongs to H, then its inverse also, as H is subgroup, so its inverse is also belongs to H. That means G2 inverse G1 is also belongs to H. So that will imply G2 inverse G2H is contained inside G1H. So equality, basically prove the equality implies this belongs to, and that will imply that it is not equal if and only if this does not belongs to. Okay, so now how can you use this one to say this is closed? Okay, so basically you consider this Q comma Q. Okay, this as a map is a map from G cross G2 G mod H cross G mod H. Okay. And delta complement, now consider this. So this is an open continuous map. Because Q is open and continuous, so just product of those things again open and continuous. So this is open continuous. So adjective also, but it will name. Okay. Now we consider QQ inverse of this delta complement. Okay. So what it consists of? So it consists of all those G1 comma G2 belongs to G cross G, such that if you map under those things, so that does not belongs to delta. That means G1H not equal to G2H, right? And that exactly from this one, you see this is G1 comma G2 belongs to G cross G, such that G1 inverse G2 does not belongs to H. That means it belongs to H complement. And now can you say why this is can you say this is open or something?
Because H is closed, so
H is closed implies H complement is open, but why this is happening in G cross G? So why this is open? So this is what, this is just like that new inverse of, yes, new inverse of H complement, or new inverse is like the previous map. So new is G cross G to G, that sends X comma Y to X inverse Y is continuous. So this is a continuous map. So H complement is open, so this is open. Open. So as this is, sorry, as this is continuous and H complement is open. This is open, and this Q comma Q inverse of delta complement is open. That does that imply this delta complement is open?
yes, it's continuous only.
It's continuous, but I'm saying like something else, right? On the right hand side I am saying this is open, but I have to say that this about the delta complement which is on the right hand side.
No, inverse image of that
Yeah, inverse
set is open. So
no, in this case it is not cosine topology, right?
yes,
Like on the right hand side I am saying this is okay, you can actually, okay, you can, okay, fine, but anyway I just wanted to use this thing openness here. So you basically on the left hand side you have this G mod this set as open in G cross G. So if you apply this QQ of QQ inverse of this thing, that is exactly this delta complement, because this is surjective. So that implies, and that is equal to delta complement, and that is open because this is open. Okay, so this implies basically what you are claiming, that to claim that you have to say that this on G G mod H cross G mod H, actually you have the cosine topology that induced from this Q comma Q. If you can prove that, that will also imply that this is open. But I don't know whether on G, because on G mod H cross G mod H you have product topology, and the individual topology comes from quotient, but I don't know as a whole that topology is same as the topology comes via this Q comma Q. If that is true, then you can also say from that thing that this delta complement is open using the quotient thing. But in this case I immediately don't know, so I just use this openness of this QQ. Okay, so when continuous also, okay, surjective I am also using. So QQ of QQ whole inverse delta complement, this thing is open, in G mod H cross G mod H. So as this is open, but this is nothing but delta complement. As this QQ is onto, right? Anything Q of Q inverse, any like whenever you have onto map, this thing is A, right? So the same thing I am using here. So this Q comma Q is onto, so you have this thing. So once delta complement is open, this implies delta is closed, and once this is closed, this implies G mod H is also open. Clear? Any question or any confusion? Okay, so then next we have suppose G is compact, then we have to prove that G and G mod H both are compact, and also conversely, if we have G and G mod H are compact, then G is compact. Okay. C. So for the forward part, let G be compact. Then why H and G mod H? So why H and G mod H are compact? Any idea?
So G mod H, we can prove
G mod
compact because this quotient map is a continuous map. So continuous image of compact set is compact.
Yes.
And it's surjective also.
Surjective is fine, right?
So this quotient group will be compact. G by H will be compact.
Yes, sure. And why H is compact? No, H is a closed subset of G, right? So closed subset of a compact set is also compact.
Okay, yes.
Yes, so that's the thing. So as H is closed subset of compact G, so H is compact. and as you say that as q g to g mod h is continuous onto so g mod h being continuous image of a compact set, compact G, it is compact. So G compact easily imply that H and G mod H are compact. So now let's prove the converse. Let H and G mod H are compact. Okay, be compact. So now I have to prove that G is compact. So now any idea about this one? So we have actually proved in the last class I have said once, and in the previous also you are trying to prove the similar kind of thing. So recall. So if G is a compact group, acting on a space X, then the quotient map Q from X to X mod G is closed. Can you recall this thing? The last thing, so in the last tutorial we are trying to prove because the normality thing. So if X is given to be normal, G is compact, then X mod G is also normal. But we already have proved in the previous thing that if you have a quotient map, like not quotient map, X to Y, which is closed surjective, closed continuous surjective with fiber each of the like inverse image of each point is compact, then we say that X is normal implies Y is normal. So we to use that thing, so here the inverse image of each point is compact, that is not needed actually for the normality, but closeness is the main thing. So in the second part we just proved that this map actually closed, and also onto and continuous is clear, so that will imply that X is normal implies X mod G is normal. So there we actually prove this map is closed. So in this case can you say that, so this Q map H to G to G mod H is closed? Why this will be closed? Like what will be the setting so that this follows from this thing? Like what will be the group action and what is the compact subset? Yeah.
H is a compact group acting on G.
Yeah. So and what is the group action? The group action is simply just left multiplication, right? Or just multiplication? Yes. Yeah. So let's say mu restricted to basically H cross G to G. Just take H comma G, multiply there H. Okay. Robertson, and H is compact. So the same proof you can just really follow here and get that this Q map, once you have this H is compact, so using that thing you can say that this is actually closed. Now you have a closed map, closed continuous onto map, and also the inverse image of each point that is compact, right? So also Q inverse of any point, let's say GH here. So this is like inverse is nothing but just as a set, it is a set, and this is nothing but GH just. Okay, so here this GH is a point, but here it is a set, right? And it is a again like continuous image of a compact set, right? Because again left multiplication is a homeomorphism, in particular a continuous map, and this is image under image of H under that left multiplication. So is compact as H is compact. Okay, so you have a closed continuous surjective map such that inverse image of each point is compact. Now my claim is that this G is also compact. So let's consider any cover of G. Let this UI, okay, let me change this to VI. UI is very confusing. Okay, VI. So VI for belongs to some indexing set lambda. Open cover of G. I have to find a finite sub. If we can find a finite subcover of this thing, then by definition G will become compact. Okay. Now for any G belongs to G, GH is a like subset in subset of G, and that will be again covered by this set, right? This, so for each thing, so as now for each G belongs to G, VII belongs to lambda is also an open cover for this GH, and GH compact. So this is compact. That means I have a finite collection of this VI that covers this small g capital H, right? So this have finite, let's say lambda G as subset of lambda such that this GH is contained inside union over I belongs to lambda G VI. Correct? So this is an open cover of a compact set. We have a finite subcover of that thing. So for each G, so depending on G, I am my indexing set will change. I am denoting that by lambda G. Okay, now all of this GH that will actually cover my whole of H. Now what I will do, I basically I'll consider this thing complement of this thing. Okay, so here this GH as an element, so maybe Q of G, maybe Q of G is nothing but that is GH, right? Okay, still I haven't used anything about the compactness of G mod H, right? So I have to somehow get a cover of G mod H. So how do we construct that cover? Okay, so basically I can say that Q of this thing, that is open mapping, so that is also closed. Okay, that I have to use that thing. So here Q of union of I belongs to lambda G Vi, this complement, so this is an open set and complement of that thing is closed set, and Q is a closed mapping, just have proved here. So Q is a closed map, so here to is a closed set in G mod H, right? As Q is closed. Okay, so once this is closed, so its complement again is open. So Q union of I belongs to lambda G Vi, this complement again whole complement is open in G mod H, and the okay, so also note that this Q of G this belongs here. So or G belongs to G. So is this clear why this belongs to here? Because initially what we had that this Q of G belongs to union of this thing, Q of G belongs to Q of this thing, but I consider only the complement of this thing. So this QG does not belongs to this complement. So once this does not belongs to Q of this complement, that means it belongs to its complement, right? So QG belongs here, because QG does not belongs to Q of the complement of the union Vi, right? So and thus, and each of these thing are open, so you can say that G mod H, which is actually union over all those G belongs to G QG, and QG belongs here, so you can say this is also union over G belongs to G Q union over I belongs to lambda G Vi, complement of this thing and whole complement, right? And open cover for G mod H. So this collection is a open cover for G mod H. As G mod H is compact, there exist G1 through Gk say belongs to G, such that G mod H is union over let's say J equal to 1 to K, Q union over I belongs to lambda Gj Vi, whole complement Q of that thing, and then this complement. Okay. Now my claim is that this G is actually union over all those J equal to 1 to K, and union over I belongs to lambda Gj Vi. We started with this thing, so so each of this lambda Gj, they are already finite, and I'm again considering finite union of those things. So this is a finite collection of the sets Vi. So if I can show this one, then I'm done. This is a finite cover, finite subcover of the given cover, this Vi, and hence G is compact. So can you say why this is true? So this set already contained inside G, so that's not problem. So let G belongs to G. So this QG also belongs to by as these sets cover G mod H, and QG is an element of G mod H. So there exists some let's say L such that this belongs to Q union over I belongs to lambda GL Vi, this complement and whole complement, right? And this means G belongs to Q inverse of this thing, right? Q inverse of, okay, this is first letter for some L belongs to 1 through K. Okay, and now this implies thus G belongs to the Q inverse of this set. So Q inverse of Q union over I belongs to lambda GL Vi, this complement and complement of all these things. Now Q inverse of some complement of some set. Okay, I'm probably missing another bracket or something. Okay, no, fine. So this complement is basically whole this Q of this complement. So Q inverse this thing is nothing but again Q inverse of Q of whole complement, right? As this is surjective. So union over I belongs to lambda GL Vi, this complement, whole of this thing, Q inverse of this outside like total outside this complement. Like in general, this is Q inverse of a complement is Q inverse A whole complement whenever you have surjective map Q. So in this case Q is surjective, so hence I can like take the inverse outside of this thing. Okay, so I'm just using that thing to get there. Now Q, I can say that G belongs here, that means G does not belongs to Q inverse of Q, this thing, right? This implies G does not belongs to Q inverse of Q union over I belongs to lambda GL Vi complement, right? So once this G does not belongs to this set, and this set is nothing but as I'm writing, this is union over I belongs to lambda GL Vi whole complement H. So in particular this particular, so this is basically union over all those. Okay, again union over H belongs to H, union over I belongs to lambda GL Vi whole complement and translated by H, right? Now so G does not belongs to this, so G belongs to the complement of this set, but complement of this set is intersection of all the individual complement, right? But here in particular E belongs to H is subgroup, so just complement of this E times that thing will be just complement of complement this thing, right? So in particular I can say in particular G does not belongs to the identity translate of this set. So union over I belongs to lambda GL Vi whole complement as E belongs to H subgroup, subgroup. So this implies G belongs to union over this I belongs to lambda GL Vi. So once this belongs to something, so this in particular this belongs to this total union, right? So thus G is contained inside union over J equal to 1 to L, union over I belongs to lambda GL Vi, right? And converse is yes. Immediate as Vi content inside G, right? Hence the claim follows. And get a finite subcover. Cover of G. Thus G is compact, right? So any confusion here? So again just recall what we did. So we started with H and G mod H are compact. Then from using the compactness of H, we claim that the quotient map G to G mod H is closed. So we actually used later on to say that the closed set here, I consider a closed set here which gets to some closed set, okay, to get a basically cover of G mod H. So then to do this thing, we first see that this inverse image of any point will look like this GH, which is a single point on G mod H, and Q inverse of that thing is GH, which is a right translate of the compact group H. So G times H is also a compact set in G. So if I consider an open cover of G, so for those will also cover each of this subset GH, and for they being compact, we get a finite subcover for each of those GH. So I am considering those finite subset as lambda G for as a subset of the given index set lambda, and now I am considering the complement of those finite union of open sets and taking Q. So Q being closed, this is closed subset in G mod H. So again the complement of this set in G mod H is open, and as G is belongs to Q of this thing, so G actually does not belongs to Q of the this complement. So If I again take the complement, then it belongs there. So for each g, qg belongs to this complement, or this big complement of the sets. And now these sets cover, each of these sets being open, they covers my whole of g mod h. Now as g mod h is compact, I will get finitely many g1 through gk, such that they covers my whole g mod h. Now I say that if you consider all the sets of vi, which comes one from like this g1 through gk many thing, and one other from this lambda gi, respective lambda gi, so those are like finitely many collection. For each j equal to 1 through k, you have lambda gj, which is a finite set, and you are considering the union over all those vi. The claim is those set will cover my g, and this is a finite subcover of the given cover. So to do that, again I just go back to this g mod h thing. So here if I pick any g belongs to g, then q of g, that is an element of g mod h, and that belongs to this union, this finite union. So it belongs to this union for some j equal to l, and then again just analyzing that thing, I get that g belongs to this union, and hence g is containing the total union, and that completes this claim, and hence g is compact. Right? So any confusion here? Okay, so then let's go to the next one. So here suppose you have connected component of a group G of the identity element E, then actually it is a closed normal subgroup of G, and in particular if G is moreover locally connected, then that the component of this is a normal open subgroup, also an open subgroup. Okay, so like there are three things mainly. So first of all, why the component is a subgroup, and then why it is closed and normal. Okay, so once you have a connected component of this thing, why that is closed? Like, do components are always closed? We have also discussed this thing previously also. So if you have a component of any topological space of a connected component, connected component are always closed? So component are by definition at the largest connected set containing that point. So component of this E means that is the let GE. So this G subscriptive. Okay, maybe just let's say U. Let U be the connected component of G containing E. So E being the identity element. So is it immediately true that U is closed? So I need to prove that U closure is U. So does that implied? Okay, so probably you just have to recall this thing. So recall that U is connected implies U closure is also connected, right? U is connected implies U closure is also connected. And E belongs to U, so E also belongs to U closure, as E belongs to U contained in U closure, and U is the maximal, like largest connected set, as U is the largest connected set that contains E. So this largestness will imply we must have this U closure is equal to U. So U closure is contained inside U, that is U equal to U closure, that is U is closed. Okay, so U is closed is not a big thing, so any component is actually in a topological space is closed. Say here we haven't used anything about the topological group. Now this component is actually a subgroup, and that's normal. Okay, so for the subgroup part, I have to prove that this new map again, if I restrict this onto this U cross U to G, again this xy to x inverse y, if I can say that this is contained inside U, then I am done. So again note that this U cross U is connected. As U is connected, so product of this two connected set, they are also connected, and this is continuous. So as this is continuous and U cross U is connected, so nu of U cross U is connected, so continuous image of a connected set. And obviously as E belongs to U, and nu of E comma E is just E, so and belongs to this nu U cross U. So this is also a connected subset containing E. So again, by maximality or largestness of the set U, this implies that lambda U cross U is contained inside U, as U is a component, is the component containing E. Okay, so this implies U is a subgroup. Okay, so now I have to prove that this is this U is also normal, right? So like any idea how to prove the normality? Like at least recall what the definition of normal subgroup. Yes.
Sir, we just sir, we did one result in which we just showed that if it is P naught, then it will be normal only.
No, okay. So okay, okay.
Sorry.
This normal, okay. This normal subgroup is not that normal. Okay, yeah, that T0 implies T3. That's saying
Okay.
this is as
But it's
normal as
very
a,
confusing.
yeah,
This
normal as a
entire
subgroup. Yes.
sometimes it's group theory, sometimes it's topology.
Yeah. Here both thing is going on. So yes, in this case, this normal subgroup is the group thing.
Now I understand the group, the normal subgroup of group theory.
Yeah. So just normal thing is okay. To prove U is normal, we need to show like the this if I consider the what I say the conjugation. So basically need to show GU G inverse. This is actually U, or all G belongs to G. This is the normality thing. So this normal, okay, normal, I should say normal subgroup. Normal subgroup. We need to show that GU G inverse equal to U for all G belongs to G. So that means if I consider this map, so that is just conjugation map. If I consider like for fixed G, that is for any G, this CG conjugation map from G to G, which sends okay, let's say X gets mapped to GX G inverse. So this is actually again a homeomorphism. So okay, I should say this satisfies CG of U equal to U. Okay. Now why this CGU equal to U? Again from the maximality, can you say something? So this CG actually you can check easily that likewise this left multiplication, right multiplication, CG is again homeomorphism. So but as CG is a homeomorphism, can you say this U is, or just continuous is enough? Homeomorphism you don't need. So CG is homeomorphism actually. This homeomorphism CG of U, this is again okay, homeomorphism I don't need, I just say continuous. This is connected, and definitely this E belongs to here because G okay, U I started with component, yeah, E contained in U. So this CG of E is E itself. So definitely E belongs here, this connected set. So E belongs to this connected set again by maximality. This implies CG of U is contained inside U, right? As U is component of U or component contained in U. Whenever you have a connected set that contains C, that must be contained inside U. u being component. Now once you have this thing, so okay, yes, so this is content inside u. Also u is a subgroup, right? So this I'm missing something probably. G is, that's it. Okay. Okay, fine. This is a subgroup, so this is G inverse is already content inside U. That is not an issue, but I have to prove this. Okay, for the equality I have to prove U is content inside CG U. Okay, CG is content inside U definitely. Okay, that I even don't. That is I can say already from, as U is a subgroup, so okay, sorry, that I'm conjugating by an element outside of U. Okay, belongs to G, so this is happening for, okay, CGU is content inside U. That thing is enough, right? I have to prove that G inverse, if I can say this is some U prime, this implies GU equal to U prime G. Now basically G of capital U is G of small u1, say, consist of u1 belongs to U. Okay, this implies G is equal to U prime G U inverse. So if I use here it, so it is just U prime G U inverse U1. Okay, for the normality I basically have to see that for all G belongs to G, GU equal to UG. That is actually equality, so I'm probably missing here. This should be okay. This should be actually content. Okay, this is actually subset. Okay, this is subset. Yeah. Okay, this is okay. This implies U is normal. Okay, so hence we have that component of this thing is closed normal subgroup of G. Now if G is locally connected, so second part, so if G is locally connected, so locally connected recalls for each point, so G is locally connected means if I pick any point from G, then it has a and a neighborhood of that point, then there is some neighborhood, connected neighborhood, that is content inside that chosen neighborhood, right? So that is locally connected. So if G is locally connected and U being this, okay, so what I need to prove? I need to prove this is a open subgroup, but we already have like prove that if a subgroup contains an open set, that is open, right? So so that means if I can prove that U contains an open set, then U becomes open subgroup, right? So but that is immediately follows from this locally connectedness. Local connected, then U being neighborhood of E, there exists connected open neighborhood, there exists connected point BD, let's say V of E, such that E belongs to V contained inside U, and U as U is subgroup, as U is subgroup containing an open set, it is open. So using like previous problem. So hence if G is locally connected, so basically locally connected, you on whole you don't need, even if it is locally connected at the point E implies this thing, but that is immediate. Once you have locally connected at the point E, you can just translate that to any point of G, and hence you get locally connected over all of G. Okay, so that's not big deal, so that's why locally connected anyway implies this thing. Okay, so next we have basically, okay, we're sort of time, so I'm just quickly go over the idea and over this thing. So suppose V is a neighborhood of E, and if G is connected, then V is a set of generators for G. So the idea is exactly like previously as we did, like for like open set generated by the subgroup generated by open set is again open. So similar kind of thing again we have to do here. So if we have a neighborhood of E V, then if G is connected, we basically will show that if you consider the the subgroup generated by this V, that is whole of G. So to claim this thing in a connected set, enough to prove that that set is closed as well as open. Then as V is non-empty, in particular E belongs to V. So any non-empty in a connected set, only non-empty set that is both open and closed is the set itself. So that will imply that the subgroup generated by this V is actually whole of G. Hence G is a set of generators for D. That's the idea. Basically you have to prove the subgroup generated by this V is both open and closed. That's the main idea here. And for the next part, suppose you have G is a connected topological group and H is discrete normal subgroup of G, then H is contained in the center. So again the center thing, so center means all the elements of G which commutes with all other element. So basically commutator subgroup of not commutator, but bit lesser. So basically all the elements of G which commutes with all other elements. So I have to show that H is contained there. Okay, so okay, so for that actually you probably need a bit thing. So let me just quickly write that thing. So you basically have to prove that H is contained in the maybe okay.
Sir?
Yes.
Sir, will you, do you have few questions related to that topic of not boundary exactly, which bounded boundary? There was
Balanced.
balanced. Yes, sir. Yes, sir.
Okay, balance actually I didn't take from the topological vector space part. Okay, but
Actually, few questions are there in assignment, and this balanced part is not clear.
like balanced is okay. How do I say this? So basically, you have a set. Let's say U is balanced in the your in the topological vector space V is balanced if you like okay, probably this is just alpha U, right? Just let me check once.
Yes, sir.
Just alpha U
We have
is
model, but
yeah, mod alpha is less than 1 and
it's a subset of U.
it is contained inside no, this alpha and basically so this okay, this alpha is just alpha is scalar, right? So this is contained inside U and mod alpha less than 1 or less equal to 1. It is less equal to 1, right?
No, sir, less than equal to.
Yeah, less than equal to 1. Okay, so okay, well, like it is this is okay, but from the definition, okay, this alpha U is alpha U just you scalar, like if your alpha, like if you consider the vector space as real vector space, this mod alpha is equal to 1. Okay, you have enough things, so fine, you just you are just translating all those elements less equal to 1 elements of U, and then you are seeing whether that is contained inside U or not. So like definition is clear, right? Like definition is not an issue, this is just
Yes, sir. Yes, sir.
so U belongs to U.
Not geometrically, but mathematically it's clear.
Yeah, like okay, like example of balanced set, you say if you take any ball in let's say in
Yes, sir.
Rn.
Any unit disk is balanced, but
Yes, like even maybe any convex set is also convex set. Okay, convex set I don't know.
sir, is like one interval minus 1 to 1 is balanced, but
Huh?
if I take discrete entries, they are not balanced, because when I'll multiply those entries with such a number, maybe those numbers will not be there. So does it mean something like, I don't know, convexity?
No, which numbers you are like multiplying not there, you are saying?
If I take any open interval maybe containing 0.
Open interval
I think
containing 0.
0.
Huh?
If I take any open interval, then for example minus 1 to 1, then
Huh?
alpha time of that interval will be contained within interval only.
Yes.
But if I'll take discrete entries in the same interval, like
Okay.
minus 1,
Yeah. So that is like that is that saying that definitely your balance set must be infinite.
infinite also, and I think all the limit points should be there, because I cannot say set of if I take rationals only, then I
Yes.
think that will not be balanced.
That is also another thing, like infinite and also limit points. Okay. Okay, limit point should like midpoint thing is not immediate. Like for the rational number thing, that is that is immediate, because you are also scaling this thing by real numbers. But for others thing, it is not immediately clear that whether balanced set are closed. Do all the balanced set are closed? I don't think so.
Those,
Yes.
because we did in this one result in class, I think if B is balanced, then its closure is also balanced.
Yeah, so closure in balance, so closure need not be yeah, true. Okay, but okay, I actually SAT didn't also gave any problem. I just basically took the problems from the from the lecture notes only. So there I didn't see any problems related to this balance set, and I'm also not much like I also haven't much used this balance set, so I actually didn't.
Okay, so then just one question.
Huh.
Can you give me any hint that if I have a continuous map and the set in codomain, if it is balanced, then how can I prove its inverse image is also balanced? Or if it is balanced, then how can I try to?
Can you repeat once again? So if you have a from some let's say view.
Vector space V to W.
Okay.
And I have a
so this is
balanced
continuous.
set in W, balanced subset.
Okay.
Yes, continuous.
Okay, so let's say this is U is balanced in U subset of W is balanced.
Then what can I say about its inverse image?
Okay, so this continuous and this is as a vector space homomorphism.
Yes.
Okay, balance. So what can I say about F inverse U? So again, just if you consider this alpha F inverse U, so this consists of all those elements alpha. Okay, it consists of alpha V such that FV belongs to U. Correct. Now can I say this alpha V belongs to this belongs to my F inverse U. So alpha V belongs to F inverse U. If I can say F inverse, so that means that is F of alpha V belongs to U or not. But you already know this F as if F is a homomorphism, like vector space homomorphism, then F of alpha is V is nothing but alpha FV, and that belongs to U. So alpha FB belongs to U as U is balanced. So alpha F of V, okay, for FV belongs to U, mod alpha less equal to 1, alpha times FV also belongs to U, right, as U is balanced.
Yes.
So and this implies that F of alpha V belongs to U. That means alpha V belongs to F inverse U, and that means this alpha F inverse alpha F inverse U, that is also contained inside, like for any V belongs to V belongs to F inverse U, you prove that alpha V also belongs to F inverse U for all mod alpha is equal to 1. So this is also balanced. So continuity is not needed, just the homomorphism part I am using here. Okay, so like these are basically you have to play with the definition only. Okay, so basically others there are some more things. So basically I wanted I might discuss this thing in the next tutorial. So these are something important you already previously said, that how to prove the connectivity of these sets. So basically these are important, and